Thank you very much, Ntate Nambani, colleagues and learners who are around. Good afternoon. Ntate Nambani will do the moving of the slides and check on other things. And I will invite the colleagues who can come in at any point, because it is not only about me and Mr. And colleagues, without much ado, Ntate Nambani, let's go to the next slide, of which it is all about the distribution of the marks, as we could maybe and plan around and see what is it that we are having. Colleagues, the paper one, it is having a total of 150. I think everyone knows. Though the topics which I have outlined here, they also include the multiple choice questions. And my plea to the multiple choice question is to say, colleagues, let's try not to give as we prepare the learners for the multiple choice question, let's try to explain to them how we arrive at the answer without necessarily just giving the answer, because it is through multiple choice that the examiners are actually trying to find the understanding of the learners. And from the onset, I can assure you that if you are dealing with the multiple choice questions, all of them, they are having the similar trend that two of the distractors are totally wrong. And then two are very close, but there will be one weight that will make it not to be true. And in order for us to address that, it means we have to be having our learners having a sound knowledge of the content. So for the multiple choice, we need content. There is no way in which we can do multiple choice without a content. And we have seen through the years that our strong learners, more often than not, they are leaving multiple choice questions and then they answer it last. And as such, time is not on their side, and then they start to just pick the multiple choice as if it is having a pattern, whereas it doesn't have a pattern. So as such, maybe let's encourage our learners to work on the time that it is allocated. So the majority, in fact, the bulk of the marks are with the mechanics, of which it is about the 4 topics or subtopics which are there, which is Newton's laws and its application, which is going to be plus or minus about 18 marks. You have vertical projectile motion, which is plus or minus 17, conservation of linear momentum, work energy and power. And then colleagues, one of the things that we have seen about this topic, in fact, all this topic or content mechanics, is our learners are struggling even to identify the formula to be used. Now, if we go to the part where we are having a data sheet, we should be using it very careful and try to attend to the learners who are struggling to identify the formula, because a formula, it is having its own mark. But we'll talk about it later. But from the onset, I should say, if you're looking, for instance, at Newton's laws and applications, on the data sheet under table number 2, there will be a part which is referring to forces. That's where the learners must be able to identify the formula which they are going to use. So we have to address that with them on the data sheet as we go on. It is not necessary for the learners to memorize the formula, because memorizing it, they commit so many mistakes that ultimately we penalize them for not having the correct formula. And there is a rule in marking that if ever we are having an incorrect formula or a wrong formula, then we shouldn't proceed to mark. It is a 0. So it is important that we also guide our learners on the formulas that we are going to use. That is the first one. For vertical projectile, it is going to be on the part where it is showing motion. And at that particular point, colleagues, we have to tell them that for that one, there is this part, because I don't think time will be on our side, that for vertical projectile motion, there is no way that they are going to be given their gravitational acceleration, because it is a constant. They must refer to table 1 on the data sheet to copy it as 9.8 meters per second squared. So it is there. And then from there, please address this with your learners that for vertical projectile motion, we are having 4 equations under equations of motion. And then for each of those equations, there are 4 variables in each and every equation. But of the 4, unless it is going to be a simultaneous equation, they will only be asking one of those variables. And then it means we encourage, or I encourage our learners to can tabulate what is it that it is given to them so that they are able to can identify the type of a formula that they are going to use for that 1 mark that we need for the formula to be there. And then let's go to conservation of linear momentum. Remember, in linear momentum, there is this part of saying define Newton's second law in terms of momentum, because we have said that the Newton's laws are part of the forces on the label of the data sheet. It means also for conservation of linear momentum, the formulas that are going to be using, it is going to be the same ones that are having under the forces. But under the forces, they is going to be one formula for momentum and one formula for the impulse. So it is important that we address that as early as possible with our learners without necessarily making them to lose marks. And then it is at this stage that I want to tell you also, colleagues, that the formula, it is not there for the conservation of linear momentum. Then the learners, from the definition of linear momentum, then it means they must derive that formula. And then for that formula, they need to put in their subscripts. If there are no subscripts in the formula, then they are likely to lose the marks. So it is important that we address that one also for the learners. And then for work energy and power, on the data sheet, it is going to be under the very same topic, work energy and power. And then usually these 4 questions that are starting, there are Newton's laws will be question number 2, your vertical projectile will be question number 3, and conservation of linear momentum will be question number 4, and work energy and power will be question number 5. So please, let's try to help them while we are still practicing towards this particular topics. And then the total mark for this part of the syllabus, it is going to be 65 marks. Of the 65 marks, the bulk of the marks will be coming from the calculations. And then it is for that matter that we have to have the correct formulas, and then we have to also to have the correct definitions to can apply to this particular work or part of work. Now let's move on to question number 6. Question number 6, it is going to be based on wave, sound, and light. Now, as you can see, it is waves, and waves are coming from grade 10. So there is no way that you are going to ignore the waves, how we draw the waves. What is it, the terminology used in the waves? We have to do it from grade 10. And then this is going to be divided into 2 parts because we are having sound and light. Now we are having to apply both to the 2 parts, light and sound. We have to apply Doppler effect. So the Doppler effect must be there, and then we need to apply it parts. Although electrostatics, it is the one that I'm saying it is going to be divided into 2, where we are having Coulomb's laws, and then we are having electric fields. So for that part, it is going to be plus or minus 20. And then your electric circuits, it is going to be about 18 marks. And then your electrodynamics, which is your electrical machines, then they will be having about 16 marks. And then the total, it is going to be 55. So both mechanics and electricity and magnetisms are carrying a lot of marks, of which our learners need to get something out of it. And then the last part, it is going to be on matter and material, where we are having photoelectric effect. And then we are also having the spectrum, which is going to be your absorption, and it is also your emission spectra, and then we'll talk to it later as we proceed. Tatina Mbani, let's go to the next slide and check what is it that our learners have to do, and also us, what is it that we have to do. Colleagues, first of all, learners must learn the theory. What we have seen in the past, it was to say we somehow teach our learners to answer the question at the expense of understanding the theory. So the theories that we are having, it is basically on the definition. So the definition statement needs to be explained to the learners. I'll make an example. If we take something like define or explain a projectile, we are saying a projectile, it is an object given the initial velocity. Now, the word given the initial velocity there, it should be saying to us and to our learners that we need to have different scenarios for us to address that one. One, immediately we are saying given the initial velocity, it means that velocity can be as we drop, and then we're having velocity being equal to 0. Or else we are going to have a velocity where we are going to throw it up, or we can throw it down. And immediately out of that, colleague, let's address it, that it means if an object it is dropped, the velocity initial it is equal to 0. It means, therefore, the object that it is going through free fall, the velocity will always be increasing, or it is going to decrease. And then reaching the ground, it should be saying velocity it is going to be increasing. It cannot have a 0 velocity when reaching the ground. So it means if we drop it and we throw it, ignoring first that part where it is reaching the maximum height, where the velocity as we throw it out, address that part, the maximum height and the velocity at the ground, so that at least we address the understanding of these learners and not get the marks as they are losing them as we see them. Now, for this, what is it that we definitions, we need to understand the theories, we need to address the principles, and we need to address the laws. Now, on the definitions, colleagues, only accept the definitions that are in the examination guideline and not the ones that are in the textbook. Some of them that are in the textbook are not necessarily going to be accepted. Now, 2, learners must learn the laws, and therefore these are easy marks for the learners to get. 2 marks are awarded for the correct definition, a law or a principle. No marks are available for the incorrect or a partially correct definition. It is not an understatement, colleagues. If we check the trend, now the definitions are saying 2 or a 0, unless there is an underlining, of which the underlining, it is just to cater for the learners, at least that they must get something, but it is not always going to be the fact. So we are moving towards that last part, that for an incorrect and partially correct definition, our learners are going to get it wrong. So the learners need to understand the definition and say it correctly about. And then based on that, it means we are saying for all the contextual questions or the long questions, we are having 9 of them in the paper 1. So we are saying to the learners, or we have to say to our learners, that we are having those 9 questions, and in each, almost in each, there is a definition. So we are saying to them, it is going to be the marks that are readily available, which is going to be 2 multiplied by 9, and then it is going to give you 18. And the minimum that we need, it is going to be 45. And then if we subtract the 18 from the 45, it means we are running short of the 27 marks. Of which part of the 27 marks for each and every question that we are having, because it is having a formula, we are also going to that part of the 27 and subtract the 9 for each and every formula that we are having, meaning that we are left with about 18 marks that we need to work on for our learners. So we can guarantee that at least half of the work is done through only definitions and the correct choice of the formulas. Number last but one, learners should be aware of keywords in each and every definitions, because if they miss it, then it is going to be wrongly marked. And then our learners will lose the marks for that. Tatena Mbani, the next one. Okay, now we go to the calculations. Like I indicated, learners must always start with the formula as it is, or the equation as it is, as in the formula sheet. So they must not just manipulate it. That is what that bullet number 3 is saying. And then marks are awarded for the correct formula, correct substitution, and a correct answer with correct SI units. If the SI units are wrong, but the value is correct, the learners are going to forfeit that 1 mark. And also, colleagues, if this is a vector quantity, then direction, even though maybe sometimes it's not marked, then it must be marked. So vectors, they must have magnitude and direction. And then I'm afraid it will be coming soon that if learners are asked a scalar, they need to show us that they understand the difference between a scalar and a vector. So ask a speed, and then we find that our learners are giving both the direction and the magnitude, meaning that that learner is not answering. He doesn't understand the difference between the velocity and the speed. So let's make them aware, because we don't know what the examiners will be having. No marks will be awarded for the incorrect or inappropriate formula and applicable substitutions. So that is the rule that I was referring to, that this must be there. And the last one we have talked to, I'm not going to maybe waste time on that one. Let's go to the next slide as we proceed with what to do and not to do. Zigo. Epa. Thank you, Baba. Learners must always, that one means the repeat of that slide, Baba. Let's move on. Okay, now let's go to the explanations, colleagues. Colleagues, the question on explanations and interpretation that are based on the theory. So it must be either a law that the learners need to use in order for them to can explain, or it must be a formula. There is no way that they cannot use it. They cannot use a formula, or they can't use a formula for the explanation. I'll make an example. If maybe they're using, they have to explain why the airbags are important, then they have to go to the momentum impulse theorem, because we are talking force, and then we are talking to the momentum that it is changing. It is important that they beef up their explanation with also the formula that they are having. And then also there, they must talk to what is it that it is going to be constant, because those questions, they are also asking about the different variables that are there. So it is important that we look at them and then we check. The other thing that we need to make use of, learners, in order for them to can understand, they need to make sketches to make things easier and feel such information as possible in their sketch, whatever is given to them. So if the sketch is not given, then they must do the sketching. 2, if objects are moving in opposite direction, left or right, they must allocate a direction before they do their calculation. But those signs, the positive and the negative, they can only be substituted. It shouldn't be on the formula. It should be on the substitution mark, because we are substituting on the direction and the value. And for that, colleagues, we have seen it, that our learners sometimes, to say they don't understand the laws. It is to say, if they are looking at Newton's second law, for instance, they will be saying, then the body will accelerate in the direction of the net force. So when they calculate the net force, their net force is going to the right, and then they allocate a positive to the right. But when they go to substitute on the acceleration side, now they put a negative all of a sudden, meaning that now they're saying, now this body, it is not accelerating in the same direction as the net force. So chances are that their substitution mark, it is going to be forfeited. So we need to address that also as quick as possible. Two, some of the questions, they will be done without friction, and some will be in friction. So it is important that the learners understand the friction. The friction is not opposing the applied force, but friction, it is opposing motion. So it is important that they look at it, because sometimes a force will be applied, maybe up the incline, but the body, it is still going down. So your friction in that particular case, it is going to be in the same direction as the applied force, because the body, it is moving down the slope, even though the force, it is being applied up the slope. So we need to look at that and take it with the learners. Number two, colleagues, it is on the interpretation and explanation of what it is happening with the graphs. So first of all, the graphs that we are having, they are having headings and labels. So the name of the graph, it is actually telling us the variables which are involved. And then the type of graphs that we are having, all of them are showing relationships. So it is important that if it is a straight line graph already, one of the questions that we should be aware of, it is going to be a gradient. And that gradient, for them to calculate, there are two ways. It is either they are using the very same labels on the y and the x-axis, or alternatively, they are using the SI units on the y-axis and on the x-axis to can calculate whatever SI units that they're coming to come up with, and then therefore they will be able to can come and do that particular part with them. And then, colleagues, while talking to the graphs, all the topics, maybe I should repeat it, all the topics in paper one, there is a possibility of a straight line graph. Every topic, go and check, then you'll see what I'm referring to. If we are looking at all the questions that we've been using in the terms and definitions, then we'll get them that each and every topic nowadays, we can have a straight line graph going through. The other type of a graph that we are not going to have, that we are likely to think a parabolic type of a reaction. Here I'm thinking of the displacement time graph. It is important also, colleagues, to talk to it and show the learners why that particular graph, it needs to be a parabolic and not a straight line graph. For a straight line graph, it is going to be only on the velocity time. It is immaterial as to whether it is for a ball thrown, it is for a ball that it is dropped, or it is for a ball that is bouncing. There will always be straight line for velocity time graphs. And then, colleagues, I'm challenging you that every time we are having a straight line graph, let's try by all means to have the learners understanding what is it that y-axis and what is it that it is on the x-axis. Whatever it is going to be a straight line, they have to go and present it in the form of y equaling to mx plus c. That one, it will help us. I'll cite an example. If we look at the formula V final is equal to V initial plus G delta T. We will have to rewrite that because on the x-axis, usually, it is going to be a time, and velocity is on the y-axis, and that velocity is changing. Now, because we are having a change in velocity, we are saying it means, therefore, that it is going to be your final and your initial because it is changing. Now, making the final velocity the subject there, then it means we have to rewrite that such that we are having that formula equaling to G delta T plus V initial. Now, that V initial, because it is where it is starting when the time it is equaling to 0, it means it is going to be our y-intercept. So we are going to look at that y-intercept, and then it is going to be the initial velocity that it is given. So if a graph it is cutting at 0, then it means the y-intercept it is equaling to 0. And then in the multiple choice question, the most popular question that it is usually being asked, it is to say, then we are going to have, or what is the gradient of the velocity time graph? Now, if a learner has written it in that form, then he can easily see that my m, it is actually corresponding to g. So the gravitational acceleration at that particular point, then it is going to be my gradient for that, in fact, my gradient for that particular graph. So it is easy for the learners to can see that. Now, if we go to our ATP colleagues, there is one bullet there that I don't know if we did do justice to it. It is saying, give the equation for an object or for a projectile or an object in free fall at any given time. So you have to give an equation for position time. So colleagues, that bullet, it means we have to look at this equation that change in y, it is equal to V initial delta t plus half G delta t squared. And then the change, let's try to simplify it to be y final minus y initial. And then we take that initial to the other side and rearrange that formula to be in the form of ax squared plus bx plus c, of which at that particular point, that part of the y initial, it is giving us the point of projection. So it means if a learner is looking at that equation, must be able to can calculate any displacement at any given time. So we need to look into those graphs also. And check if we can come up with a straight line graph, we can come up with a parabola, and sometimes we need to come up with a hyperbola, colleagues, because we are having relationships. For instance, in your Coulomb's law, in your electric field, where you are having the x squared or the distance squared. So we need to look at that one also, about the relationship and the plotting of those particular graphs there. And then, colleagues, can we make it, as we do the calculations and everything, that our learners tend to write, especially what is it that they are looking at? For instance, if they are looking at voltage total, let them write I total will be equaling to V total will be equal to I total multiplied by R total. And then the R total then will explain that it is going to go to the external, all the total in the external. So meaning both the parallel the top of W net, the net means we have to add either the works or we have to add the forces. So the subscripts are very important when we talk to the calculations and the substitution, so that our learners can get whatever it is that we want to have with them, and then we proceed. Ntate Nambane, the next one. Zigo, are you there? Okay. Hi. Are they repeating themselves or are they slow? Okay, Baba. All right. Yes, Bob. That is the first part that we are looking at. Now, colleagues, with Newton's laws, our learners are expected to know the 4 definitions of Newton's laws. That is our first law, second law, third law, and the gravitational law. Those are the 4 definitions that are expected of them. And then based on these, colleagues, it is also important that we look at Newton's third law. Specifically, I'm going to refer to it. In the multiple choice, our learners are making a terrible mistake, because if we're having an object that is lying on the table, we are having the normal going up and the gravitational force going down. They tend to think that that particular forces are going to constitute part of the action-reaction pair. So it is a challenge that we are having, that our learners need to understand the difference of, in fact, the definition of different kinds of forces as they are coming from grade 11. Remember, weight, it is a force that the earth, it is exerting on the object. So it means the reaction to that, it should be the force that the object is exerting on the earth, because you are talking there 2 objects there. And where is this coming in? Please, colleagues, we have to have 2 objects there. So each object is having a mass. And then also on Newton's law of universal gravity, there must be 2, at least 2 objects which are there. So that means this part of Newton's laws, we need to distinguish that for Newton's first law, we concentrate on 1 object at a time. And in Newton's second law, because it's a special case of Newton's first law, then we also look at 1 object at a time. Even though the question might be simultaneous and we have 2 objects, but we are looking at 1 object at a time before we can do any other thing. From here, I will be saying to you, it is important that when you go to number 3, drawing of free body diagram and force diagrams, it is important that even if not asked a question on the other, we need to draw that other body if we are having 2 objects that are there. And then when doing calculations, colleagues, that's where they're going to be distinguished. You are Newton's first law and Newton's second law, because the calculations are done on the objects or on the forces that are in equilibrium and on the forces that are not in equilibrium. So basically for equilibrium, we are looking at Newton's first law, and then for non-equilibrium, then we are looking at Newton's second law. And then at this particular point, colleagues, it is important that we look at what is it that we are having on the objects. And then we are going to have either a single object moving on a plane with or without friction. It should be on a horizontal, inclined, or a vertical. And then, colleagues, please check the examples that are given. On the incline and on the horizontal, we have been using this for some time. The lift and the rocket, it doesn't mean it is not there. We need to look at the rocket, and then for that one, especially the second phase of the rocket, we need to address that one also. So basically, this is what we are having for Newton's first law when we are looking at the single object. Now we are having it on 2 objects that are numbering. The first part will still hold, but what type of system are we gonna have? We must have 2 objects that are joined by light inextensible string. And then in this case, that is what I was saying, that we need to apply Newton's law of motion on separately on each. Why? If the learners are going to apply the systematic approach, then they are going to get at least, if the question as a whole, it was 6 marks, chances are that they are going to get only 1 mark for the formula and then 1 mark for the answer. If the substitutions are not there showing the interaction between the forces. So it is important that we refrain from using the systematic approach. Systematic approach, it is a recipe for the learners. And colleagues, I usually say to the learners, I know the learners are how they are. We'll be asking them that the answer will be 2. We can even check with them. If we take 4 and then we divide it by half, the answer will be 8. And we take the very same 4 and we multiply it by 2, the answer will be 8. So it means they need to look at the operations. We are not interested in the answer. We are interested in the skills that are being asked. Hence, the substitution, it is very key, and the operations are very key. So if we're looking at 2 systems, we have to look at them both on a flat plane, with or without friction, or even here, if they are on the flat surface or horizontal, the force might be horizontal or it might be at an angle. So it means also here, we need to re-emphasize the issue of resolution of vectors into components. But when we draw free body diagrams, colleagues, we are not accepting any components. Our learners will lose marks. 2, we can look at a situation where one is on horizontal with or without friction, and then the other one, it is hanging vertically from the string over a frictionless pulley. Or we might have both on an incline with or without friction, and then the angle of the force can be the same on the same plane, or it can be at another plane. Number 2, both hanging vertically from the string. And then that last one, colleagues, is very tricky for the learners, because as we release them, one will be going down, will be accelerating down, and then the other one will be accelerating up. So it means on their substitution for the acceleration, they need to show that one, it is accelerating down, and then the other one, it is accelerating upward. So it is very important that we look at the sign convention that we are applying with our learners. Next slide, Baba. Let's go to momentum. On the issue of momentum, colleagues, the slides will be there. Father Nambani, yes, yes, Baba, those are the ones. Colleagues, momentum, we have to describe it as a vector nature. It is important. We look at the definition and then describe the linear momentum. And then we draw the vector diagrams. And then, colleagues, that bullet, there it comes, Newton's second law in terms of momentum. And then this one bullet there, it is the one that it is talking to the issue of the seat belts, even though here we are just putting it, because there will be a net force that it is going to be there. The issue of seat belts, the issue of crumple zones, the issue of arrestor beds, all those, they are coming through here. So we need to look at them. And then, colleagues, also here, because of the net, it means sometimes when you apply the brakes, now friction becomes a net. We have to look at it that now the direction, what is going to happen here, then we look at it. And also, colleagues, let's look at how we draw the vectors. It is a typical multiple choice question that we can have on the drawing of the vectors. And then, colleagues, the issue of definition of a momentum, it is as in the formula sheet. That is one equation that we are having, that P is equal to the product of mass and velocity. Our learners must get it if it is asked. Let's move to the next one, Bob. Time is not on us. Let's go to impulse. Also on the impulse, colleagues, we need to look at impulse, the definition thereof, and then how to use the impulse momentum theorem. This is what we are referring to. Use that one and explain how this concept of impulse is implied to safety considerations, like we are saying. And then, colleagues, the part which is in broad, that conservation of momentum, and then the elastic and inelastic collision. What is expected of us? It is to explain the system. And then when you talk of that system, we are talking of an isolated system and not a closed system. We isolate it. So closed, it is used in chemistry. Here we are using an isolated system. And then we have to talk of the internal and external forces. And we have to explain also what we mean by a system, because a system, like we are saying, it is a system when we are dealing with Newton's law systematic approach. What do we mean by that? The principle of conservation of momentum, we need to look at it. Now, the application, it is on linear momentum to collisions of two objects moving in one direction. Meaning what? It doesn't mean one direction here means one body can be moving to the left, and then the other one, it is moving to the right. So the direction here, it is on each and every object. Not necessarily that the two will be following one another. And then we have to distinguish between elastic and inelastic collision. Going back to the September, colleagues, I'm not maybe rubbing salt into your wounds, but this is the question that we ask: distinguish between elastic and inelastic collision, but we put it in another form where we know that it was a mechanical energy that it is there because it is on the ground, and there at that particular point, there is no height. So we tend to think of what is it that these learners know and not know. That is why we put that question in there. Next one, Baba. We go to vertical projectile motion. For vertical projectile motion, colleagues, there are a lot of definitions there that we need to use, and also the application thereof of the formulas that we need to address. I talked to it, but we need to look at them. So definition of a free fall, colleagues, and the explanation of a projectile. Free fall as a definition, immediately, it's a motion. Immediately, we have seen it, that now the learners are saying an object moving under the influence of gravitational force only. For the fact that he started with the object, we tend not to give a mark. So let our learners refrain for free fall putting the weight object there. They should start first by motion of the object. If we start with the other way, you can hear the order. Object moving under the influence of gravitational only. That is going to be a projectile. So motion of an object, it's a free fall. But if I'm saying an object, that means now we are looking at the projectile motion. So then for free fall, refrain from using the weight object there. Now, colleagues, when you go to the equations of motions, I think I've touched on them, that the learners, they must use the variables as they are. And then, colleagues, if we can, where possible, because here we're talking of gravitational force as the only force that it is acting for this topic. Let us maybe restrict our learners to the first three equations. That last one, where we are having change in y, it is equal to v final plus the v initial divided by 2 multiplied by delta t. Our learners are making a mess there. Instead of putting a plus, they're putting a minus there because they are so used to change. So it says to us, therefore, that then that formula, it is wrong, and then our learners are going to lose marks there. The other thing about that formula, which I don't like about it, it doesn't contain gravitational acceleration. So somehow, somewhere, our learners are making a lot of mistake about it, that formula. So my advice will be to say, let us try to help our learners with the three that we are having, and then the answers will be correct. In case you are not having any acceleration, then at least, colleagues, let us look at it at the other point. Now, it is in this part where we are having problems of objects having moving up, down, and then the issue of direction is coming in. Of giving you a graph at any point, and then we need to, if we're looking at those two bullets there, that they can give it as a positive or a negative gradient. So it is not safe to can say to our learners that always G going down is negative, because examiners can give it as a positive value, depending on what is it that they're having in their minds. So our learners are expected to do calculations using those equations. They're expected to sketch position versus time graph for objects thrown, for object released, and then for objects that are bouncing. And then the learners are going to either be given the graphs to can determine the position, the displacement, or the velocity time. Mr. Nambane, I don't know, I was dismissed. I'm back, but I rejoined. So, colleagues, yeah, let's try again to look at this. And colleagues, when we are giving these graphs, let's try to explain to them, what is it, the variables. Basically, the graph interpretation is all about variables and what type of a shape of a graph that we are having. So velocity time graph, like I indicated, is a straight line. But position time graph, it is going to be a type of a graph where we are going to have a parabola. So let's stick to those and try to help our learners that they cannot just draw wrong graphs. And then let's move to the next one, Bob. Work energy and power. As you can see, I'm rushing. Time is not on our side. For work energy and power, colleagues, there is a definition of work that we need to do. Also, at that particular point, even though the question, colleagues, didn't ask the learners to draw free body diagrams, let's encourage them to draw free body diagrams here. And also to resolve this, because they need their calculations. And then now of late, the questions that we are having, they are saying we need to distinguish, in fact, use energy principles. Energy principles are work energy theorem and work done by non-conservative forces. So conservation of energy, it is very key. But talking to the two, they are exactly the same. It depends on how you look at them. But for work energy theorem, if it is on an incline, it is very important that you resolve that weight into its components. And then the learners must have for the net to look at each and every force that it is acting along the surface. And then they have to look at the cosine of that particular force, either a 90, a 0, or a 180. This is your work energy theorem. And then in this particular case, I'm referring that directly because I'm saying we need to resolve the weight. So it means for that one there, we can use components as they are because we have resolved. But when you go to NC, which is your work done by non-conservative forces, we are not using the components of the forces. We are using the forces as they are. It is very important that we look at this. And then the only part that I can add to this is most of the questions that we are asking on NC, we are using the contact forces. Because the non-contact, which is going to be gravity in this particular case, will be taken care of by that change in potential energy. So it is important that we look at that. And then the other thing about this part of work, colleagues, it is on the definition of conservative and non-conservative forces. It is a force, but if the weight work is not there, then it is 0 out of 2. It is a force for which work done in moving the object between 2 points. Then it is either dependent or independent, depending as to whether are you talking of conservative or are you talking of a non-conservative forces. So it is important that we look at those and then we come up with whatever we can have for our learners. And then for that part, we have to look at what is it that being for our learners in order for them not to get 0 out of whatever we are having. So we need to work into those, and then we leave no stone unturned for the learners. So for this one, we use the forces as they are, no resolution here. But with the work energy theorem, then we have to resolve that particular those particular forces there. That is basically what we need to look at. The next part that we look at under work energy and power, it is going to be power. But before I go, on that definition of work, colleagues, remember work it is equivalent to energy. So the way we write work, W equaling to force delta X cosine of 0. I say, please go back and talk to that cosine of 0. That cosine of 0 or of theta, it is the angle. That angle is between the force and the displacement. If they're in opposite direction, then it is going to give you that 180. But if it is on the same direction, then that's where the 0 is. So please emphasize that it is the angle between the displacement and the force. And then if it is going up and then the force is horizontal, then that means it is going to be 90. That is the angle between the two. Then it is going to be no work, it is that. And then hence, here we have to distinguish between positive, negative, and 0 work. We have to do it as that bullet number 4, it is talking to that particular point there. Now, the next part that we are coming to, it is going to be on power. Colleagues, the definition of power, I put it also as an equation to can say in weights, but if learners are looking at it there, they can see that if we are telling them that dividing by time, it is a rate, that means then power will be the rate at which work is done or energy is being transferred, because to do work, you transfer energy. So these are some of the definitions which we should maybe circle as we put it with our learners, that this is one equation where it is also giving you the definition of what we have to work on. And then we have to do a calculation of power when work is done. There is no power calculation if no work is done. And then we have to talk to average power. When are we doing this average power, colleagues? We are doing average power on objects that are moving at a constant velocity. And then that is where that particular formula, which I don't like, it is coming in. Because the average is going to be saying we are having to add, if we are having final and initial velocity, then we have to do that. And then we have to also divide by 2. Ntate, I see a hand from Bokamoso. Is it, or is a legendary hand? Okay. Now, the other thing that we need to look at that, colleagues, we have to look at that power with a constant velocity along a rough surface or a rough horizontal, or we have to look at it on an incline. So power can come in at any point. And then we have to also look at a power through the output of a pump lifting a mass of water, or whatever through whatever height that we are having. Now, colleagues, I'm looking at the power output there. Immediately, even though it is not been saying this we have to do, but to me an output is saying two things. That for the output to be there, there must be a mechanism that it is going to bring in or bring out about that output. So the output that we can have, it is a windmill because it's a mechanical way. It is going to be where your machines will be coming in. So electrical motor, it is part and parcel of this output that it will be there. So it is very key that already it is saying to us, please look at me. There is a possibility here of an integration that it can come out at this particular point there. So my colleagues, I think you are look at these things and what is it that maybe tempt us to can say now we are bringing in an integration. And then an integration, colleagues, will always be there, because if we look at the whole of mechanics, it is all about forces. And once you are looking at forces, then means you are looking at Newton's laws. And under Newton's laws, it is everything that you are looking at here, that it is going to be there. Your momentum is there, your collisions are there, everything it is here. So that is why this part, there will be a lot of integration that it is possible. And any other topic where we are having a force and where we are having a force from grade 10, grade 7, that a force, it's a push or a pull. Once you pull on something, then there will be a change in position. So that is why it was not something that was strange to say last year in November in Photoelectric Effect, because the electrons were embedded. But when light was thrown on it, they start to move. An electron, if it's having a velocity, an electron is having a mass. That means it is saying to us that there is a mass multiplied by velocity, which is going to be a momentum, and then therefore then integration will be there. So integration is everywhere, colleagues. We cannot run away from it. Tatina Mbane, let's move to Doppler effect, which is wave, sound, and light. Colleagues, stating Doppler effect, even though it is a very long definition, we have to do it for our learners. And then let us explain that change in pitch, that the pitch, it is affected by the frequency. That is the change in frequency that it is there for the pitch to change. It's not anything, and then it is coming from grade 11. And then for that, we can have either an object or a source is moving towards or away. Now, in this particular case, colleagues, because we're having two scenarios here, there is a possibility also of a simultaneous equation. So let us look at it, and then we look at what is it that we are having. Colleagues, for this formula here, let's encourage our learners to first write it as it is, as in the formula sheet. And then the next step, it will be then that they can put it in, maybe eliminate the plus and the minus. But if they are not writing it this way, and then they tend to write maybe V minus whatever 0 there, and then the listener, it is stationary, then they're going to forfeit that particular mark. If ever they are putting it as a derived formula, anything that is stationary must not be part of that particular formula. Hence, we are marking it wrong. If the listener is stationary, then above the line there, we only look at V divided by V, and then it is either going to be plus Vs and then multiplied by Fs. If they are not going to do that, chances are that we are not going to award any mark to that one there. So the Doppler effect, colleagues, bygone are those years where we have to think of Doppler as a giveaway mark. For some years, I think we have been seeing that there was a graph interpretation on this, where we're having maybe parallel lines. And in 1 year, there was a straight line where there was asking about the gradient of that particular graph. So like I indicated, this particular topic also, we can have it in the form of a straight line, and then we can be asked any other interpretation about it. So no topic is easier these days or these days. So we need to look at it. And then let's go to the red shift and the blue shift. Colleagues, even though it is 2 marks, it is important that we do it. Think of it where you are having a learner who is having 42 marks, and then he's just running short of explaining that now the spectral lines are moving towards the red end of the spectrum. Not necessarily the red lines or the red spectrum is shifting. It is the spectral lines that are shifting either to the blue end of the spectrum or to the red end of the spectrum. And also the uses of the Doppler effect in medicine and then in transport, like where we are having the radar guns and then the Doppler flow meters. Those things are what we need for our learners to get the 2 marks from them. So we need every mark we need. The learners have worked through it for the whole year. So we need to look at that particular point, and then we need to have the marks for this. Let's move on to electrostatics. And then under electrostatics, we divide it into 2 colleagues. We are having Coulomb's law, and then our learners need to look at Coulomb's law, colleagues. In the definition, they give out the product of the charges. They are directly proportional. And then because we are having them directly proportional, we still have learners who are saying that directly proportional to the product of the charges and indirectly proportional to the square of the distance between them. Colleagues, it is not going to be right. We are not doing English direct and indirect speech, unfortunately. So they lose 1 mark. So please take note of that. And then we are going to use the equation to solve this for charges that are in 1 dimension. And then if it is in 1 dimension, colleagues, the maximum that we can have, it is going to be 3 charges. They can be 2, but we can have also 3. So go and do this particular part where we are having maybe Q1 and Q2, and then they put in another charge at the left or at the right, or they just put it in the middle of that, and then they want us to calculate the net force. So all those scenarios are in terms and definitions. Let's do that. Or else, if they are now they must be at right angle in the vertices of a right angle triangle. So we need to address this part, colleagues. And then we go to electric fields, colleagues. We don't have to look much to it, but it is disturbing that our learners are losing a lot of marks in the definition of electric field. Electric field as a region of space where I put it deliberately in this particular case that we need to look at this, that I put a Q, capital letter Q and an F, where a charge is going to experience a force. It's a region because it's an electric field just in general. And then if we look at bullet number 3, electric field at a point. Now the difference is that small letter Q, it is a positive point charge will experience, and then it is there. It is a positive unit charge will experience a force. So that is the difference between the two. So we talk of a region, and then here we are talking emphasis on an electrostatic force. charge is going to experience an electrostatic force. So let's look at that particular point, colleague. And then because of the calculations that we are having, now we are bringing in this other equation that can SJ please switch your mic? Thank you. And we solve we solve problem using this equation. Why R squared, colleagues, is because then we are looking at it, placing at that particular point. So that particular point is telling us the distance. So instead of R there, it can be a D. That's where this part is coming in. And then what is not right, our learners are not doing right, is to look at electric field as a vector quantity. It is a vector quantities because the electric field lines are always starting. We are giving it a direction, always starting from a positive and they go to a negative. Immediately we are saying from positive to negative, then it means we are giving it a direction. So electric fields are actually vector quantities. And then, colleagues, that bullet number 2, draw electric field lines. I don't know what is happening now. Draw electric field lines for a single point charge, of which can be positive or negative, and then 2-point charges, which can either be both of them positive or negative, positive, both of them, or we can have both of them be negative, or we can have a positive and a negative. And then on this one, colleagues, where we are having a single one, if it is a negative, now the field lines need to come into the sphere. And then we know it is going to be 3 marks, colleagues. That 3 marks is very important. The direction and then how are they radial? So let's help our learners. And then when we're having 2 charges, what is it that they're looking at? They're looking at the direction. They're looking at how are they curved in the middle, and then how are they curved on the outside. And also this goes for a charge sphere. So we need to look at this, and then, colleagues, we need to address everything that we have about the electric fields. Now let's move to the next part, which is going to be our electric circuits. Now in the electric circuits, colleagues, maybe I will be just rushing through everything. But for electric circuit, colleagues, for your learners, you can just use only one formula for the calculations. That Ohm's law formula, colleagues, it is universal. Work energy theorem, it is universal in the work energy and power. So what is it that we are looking for here? Stating of Ohm's law in words. Our learners, colleagues, our learners, leaving out constant temperature is costing us a mark. And then I think very soon this definition will be 1, or it will be 0 or 2 if we are still marking it as 1. Now we have to have this particular relationship. We need to talk to them. Current, potential difference, and resistance. And colleagues, one of the things when I talk to these relationships, even though we are looking at them, it is not always going to be that it is going to be a straight line passing through the origin. Sometimes it will not be. The other thing about this, it is not always that V will always be on the y-axis. It can still be on the x-axis. And when we do it experimentally at schools, I think what is it that we are changing? Especially in lower grades, we are changing the batteries. And once you are changing the batteries, that means your battery, it is an independent variable. And because it's an independent variable, that means it is going to be on the x-axis. And then the current that you are getting there, it is going to be a dependent variable. So the gradient of that particular graph is not going to be a resistance, but it is going to be 1 over resistance. So we need to look at those, and then we come up with correct relationships. 2, we need to differentiate between ohmic and non-ohmic conductors and the conditions, and then also give example. Things like copper, things like nichromes, things like gold, this will be coming in. But for now, we are using conductors. So we need to look at this. And then what is it that we are going to use this formula from, or the Ohm's law we are using for the networks that we are having? The parallel and the series, and the maximum that we can come up with, it is for resistors, excluding the internal resistance, colleagues. That is what we are going to have for this particular topic here. So now my advice to you, whenever we're going to do about this topic, it is for us to use only one. And then if we are talking R here, if it is R total, then it means it is going to be V total, and then the current is going to be total. If we are using it for 2 ohm resistor, I'll put a 2R for R2 ohm, and then my potential difference will be across the 2 ohm resistor, and the current will be the 2 ohm resistor. Hence, I said it is important also to look at the subscripts, introducing the issue of subscripts when we do the calculations for our learners. Let's move to power, Papa. On the issue of power, colleagues, we have to have power, a definition thereof, and then solve problems using this particular part. Remember, in the previous one, it was on work, energy, and power, but here it is electrical power. So there is no way that, because it's electrical power, we cannot use the variables that are involved with electricity, which is going to be a potential difference, your current, and your resistance. Hence, all these equations are all about the power there. So meaning, what is it that I left out earlier was to say, maybe when you go to that table, it is important that we guide our learners which formula. These ones here, they will be under electric circuits. There is nothing that these learners cannot do about it. And then from there, colleagues, we have to solve problems involving the constant electrical energy. Kamohelo, your hand is up, you can come in. Unmute and come in, Baba, or me. Kamohelo. Okay, Baba. And then from there, because of electrical power and electrical energy, colleagues, then the issue of costing, it is coming in. And then the issue of costing, colleagues, we tried our best during our September noted Esther to can say, colleagues, if we think carefully about how that question was phrased, it was to say, colleagues, in our household, we are using televisions, we are using lights, we are using fridges and everything. So the appliances are the ones. So the costing, as we are doing it in grade 11, it is an introduction that at least we can able to calculate. But the electricity that we are buying, of which we are having a cost on, it is operating on RMS values. So it is important that we look at it positively and say, what is it that it is happening? During the load shedding, it was a usual thing to say, switch off all your appliances that you are not using, so that the energy consumption is becoming lower, and as such, you will be losing. Even now we are still saying, if you are not using a fan, just switch it off so that at least you are saving on it. So the values that we are using are actually RMS values. That was the reason why that particular question, it was put here and not on an electric circuit. Can we take a standard day and then we proceed? Colleagues are showing up. Okay. Now, colleagues, I just put it there that we are having costs, the equation or the formula as it is, because it is not in the data sheet that we talk to it. The way it is kilowatt hour. Now, immediately we are having at that, the kilo, we have to put it into that. So whatever power that we are having. We are having power measured in watts, but the hour, it is actually a unit of time. So basically, we are buying energy and not power, because power from the formula above there, it is equal to W by T. But if I have a unit of power and you multiply by time, basically we are buying energy there. So we have to have that energy. So this formula, we can reduce that. It is energy multiplied by the price that it is there for the unit, which is a kilowatt hour that we are having. Then our learners must get at least something out of this equation there. And then, let's proceed. This one, colleagues, the internal resistance and the parallel, that is basically what we are having. Colleagues, the definition of EMF, it is also in the data sheet. That formula, V equaling to W over Q, that is the maximum potential difference that we are having. That is going to be the maximum work done per coulomb of charge, as it is there, W all over Q. And then this formula here also can be used to explain what is meant by 12 volts. So your 12 volts, it is going to be 12 joules, because W and energy are the same. So it is going to be your 12 joules divided by a coulomb of charge. So this formula, which is in the formula sheet, it is addressing this. Now here, colleagues, the only problem that we are having, it is on that part, solving the second problem. Colleagues, the easier way to solve the second is to identify the total current. And once you can look at the total current, your learners will never go wrong. Because if you go to the battery and you identify the positive and you track down the current, let your learners use different colors for the current, so that at least they can trace that as I move from the positive, I have one path until I reach a point where it is having a split. And once there is a split, then they must be able to identify that at that particular point, because we're having a split, then we'll be talking of the parallel combination that it is going to be there. And then on my load there, it means I must go and calculate the potential difference wherever I come across a resistor. Then there must be a potential difference there that I can calculate. There must be a formula which I'm going to use to can calculate that potential difference. Because I'm having, that resistor is having a value, there is a current there. That means, therefore, that Ohm's law equation, it becomes a very handy tool to can use here. So the easier way is to use the that formula for Ohm's law to calculate any circuit. It is very easy. Then we'll get it. Now, what is going to happen? It is the same. We must expect that there will be some resistors that are going to be connected in series. There will be some that are connected in parallel. Though, colleagues, it doesn't mean that we cannot have all four connections being in parallel or all four being in series. They can be. So it is just a matter of what is the taste that the examiners want to feel, or maybe the cake that they want to taste at that particular point. Now, colleagues, let's move on to the next one, which is going to be your electrical machines. Electrical machines, colleagues, energy conversion. Colleagues, let's talk to it. Immediately we are saying for a generator is going to produce current. Now, current, it's an endpoint. Current is an electrical energy. But for it to be there, practically what is it that is happening? On the generator, before you start it, then we have to pull that wire so that there must be a rotation. The learners must realize it. Let's make it practical. Now, immediately we are applying a force in a particular direction. Now I'm seeing it pulling, then that rope, there is at least a bit of an extension on that rope. meaning that there is a change in displacement, and then it is in a particular direction. So because of that, it means there is a work that is being done. What type of a work is done? Then there is a mechanical, because you are having an external force that is coming in there. So there is a mechanical energy which is converted to electrical energy, because if that one is not there, the mechanical energy is not there, there will be no electricity. And what is the function of that? It is just to change the flux that it is going to be along the magnets there. And once we change the magnetic flux, then we talk of electromagnetic induction. And that part, it is coming from grade 11. Remember, in grade 11, you're having a solenoid. You are moving the magnet in and out. As you are moving the magnet in and out, you are changing the flux because of the cross-sectional area of that solenoid. Number two, if you are not moving the magnet, then we have to move also what? The solenoid can move. And then what is it that it is happening? Then there is a reading on the voltmeter, or there will be a light that will be coming in. So colleagues, we need to talk to this. And then that, if we are looking at the generator, we are talking of a magnetic induction. But if we are looking at the motor, what it is there, it is not electromagnetic induction. It is going to be a motor effect, because already we are having a current, and then that current will make it to rotate. So it is the opposite of a generator. You must have first the current that it is going to move. So we are moving from electrical energy going to a mechanical. So that part, it cannot be the same as we are having mechanical to electric. Hence, it is going to be very wrong for motors. The energy conversion that we are having is the same as that one, and then the principle being used there are going to be the same. So in the motors, it is going to be a motor effect, whereas in the motors, it is motor effect, and then in the generators, it is going to be the electromagnetic induction, or the so-called Faraday's law. Then we accept. But Faraday's law is not a principle. Principle, it is electromagnetic induction. And then colleagues, the other thing, we have to help our learners in getting this easier mark. How will the coil rotate? The motors, being it a motorbike, being it a motor car, any type of a motor that they know how big it is or how small it is, always there is a rule in South Africa that they need to keep left. Because of that keeping left, then our learners must know that the motors we have to use Fleming's left-hand rule to can determine what is it that it is happening. And then usually, colleagues, I'm saying, you look at your hand and the fingers that you are looking at. You are having 5 fingers. Finger number 3, when you count, it is central. On the other side of it, you are having 2, and on the other side, you are having 2. But that central one, it is important for me to say it is central, because that central is starting with a C. And then the variable that it is going to be associated with it is going to be the current. So it is C to C. And then the fourth finger, it is pointing at F. What F it is there? It is going to be your field, FF. Field. What type of a field? Then it is going to field. It is moving from north, it is going to south. And then the thumb, which is the T. The other weight for force, we call it a thrust. It's starting with a T. So those fingers there, they must point in the same, in the correct direction for that. And then for the generators, colleagues, you can see there, generator is having a G in the middle. Generator, that G, capital letter G. The only hands that we are using, it is left and right. So in the right, there is a G. That G is telling me that for my right hand, I have to use a generator. Fleming's right-hand rule, I'll associate it with the generators. And then the left hand, I keep left, then it is for motors. There are hands there. Maureen? Colleagues, there is another in there, Baba. Rababedi. Okay, Baba, let's move to the next one. Now, colleagues, it is on these issues where we look at the alternating current. Now, the alternating current, colleagues, it is, as it is an AC. We can see it's alternating current, and this is what we expect of our learners. Advantages of alternating current over direct current. They must know that it can be stepped down for transmission at low energy, at low heating effect. All those, they must come in. But importantly, it is sketchy, the voltage versus time or the current versus time for an AC. But colleagues, because of the interpretation, all these bullets are coming from examination guideline. But because of the interpretation that if the shape of an AC, we are saying it is alternating, meaning that it is moving from positive to negative every time it is changing the direction, because we are using direction signs, positive and negative. What about the direct current? Now we are saying it is in a uniform. So that means we have to have only one direction that it is there. Hence, the examiners, because of that rule of interpretation that it is there, learners need to interpret the graphs. Then remember, in another bullet above, it was saying learners can sketch, learners can interpret. That is why in some instances, we find them being drawn, and then in some learners are expected to draw those. So it is important that we do them both, colleagues, and then we let them calculate. And then, colleagues, this definition of terms of alternating voltage and RMS for the current. If the learners, maybe for voltage, they are using current, it is the current, they'll be saying RMS voltage, it is the current, whatever. Once there is a mix of voltage to current or current to voltage, then it is going to be zero. They need to talk to what is it that it is being asked. And then it is not sufficing to say it is the maximum current divided by square root of 2. No, we look at the issue of saying it is going to be the energy dissipated or whatever, the energy that is going to be produced, of which it is going to be the equivalence of a DC. And colleagues from last year, in fact, from last year and this supplementary, if the learners start with a DC, then they were getting it wrong, because it is not really the DC, but it is the AC that dissipates the same amount as a DC. So please, the order there must be correct for our learners there. Then we can use Ohm's law in whatever form to can calculate the average power. Now, that first one where we are having P average, sorry for the subscripts which are not there, being equal to IRMS multiplied by VRMS. If the learners there, they don't put those RMS values there, colleagues, it becomes a trouble. It become troublesome, because we are talking here of the power dissipated by an appliance, and those are using RMS values. So if the learner is just using it like in any electric circuits above, where we are using it in Ohm's law, they're putting us in a very awkward position. And then I don't know for how long will it be accepted with Umalus that we can ignore the subscripts. So in this particular point, please, colleagues, let's indicate to our learners when they arrive at question number 9, the subscripts are very important. And then at question 8, which is electric circuits, there are no subscripts there. The only subscript that we are using, it is going to be the subscripts that are referring to, for them to make it easier, what is it that they're dealing with. But here, they must do it. And then that other part where we are having P average equaling to half multiplied by I max multiplied by V max. That is just because of mathematics. But both these equations, they must be for purely resistive circuits where we are having resistors, because we are going to use resistance also, and then Ohm's law, it is coming in here. So that is basically what we are having for this. So please, colleagues, let us try and look at all these parts, and then we are there. Cynthia, your hand is up.
Good evening, sir. So I would like to ask, are non-ohmic resistors essentially false?
Non-ohmic resistors are the resistors that are not obeying Ohm's law. In other words, when the temperature is changing, they are also deforming. And then as that, when we plot them now, we will see that the potential difference or the current will start, that relationship is starting to curve. So those are going to be things like your nichrome wire. The nichrome wire, when the current it is passing, then it becomes water and water. So that means the energy or the temperature is not constant, it is changing. Whereas with copper, even if you can, it's becoming hot, but it's still going to obey the Ohm's law, that it is still going to give you that gradient which is not changing. That is the difference between the two. Are you okay, Cynthia?
Yes, sir. Thank you, sir.
Thank you very much. It is my pleasure. You can lower your hand if you are done. And then let's move to the next one. The next one, that number is going to be question number 10. And then for this one, colleagues, there is a hand at Castlebridge. Castlebridge. Okay, lowered. Colleagues, for this question also, please, let's try to help our learners and redirect them. Which formulas are we going to use? And then there's Pechu, or is Petunia maybe? Pechu, your hand is up, you can come in. Pechu, okay, all right. I was saying, Baba, for photoelectric effect, which is going to be question number 10, our learners need to understand that this particular topic, the formulas are not going to be the last. They are just in the middle. They are found under wave, sound, and light. That's where they're going to find these equations which I put here. And it is important that they look at them from that. And then for this, they need to look at it that photoelectric effect, it is actually used to demonstrate the particle nature of light. Why the particle nature of light is because on the formula, we are having that energy, which we call a photon, which is a packet of energy. Because it's a packet, then it is giving us that particular particle nature. It is not the wave nature, because we are not going to talk of it. Even though we apply light, we are not going to look at what is happening. Things like refraction, reflections, and all those, they are not going to be here. So it is going to be about the particle nature, and then getting to know that energy. And that energy can be in between any form, where we are having E equaling to HF or E equaling to HC divided by lambda, depending on how you are going to calculate it. And then I'm leaving it to our teachers to can explain to the learners the effect of intensity. The intensity, colleagues, we are not changing the frequency, because frequency, it is associated with the very same light. So the frequency, it is about the color of that particular light. So we are not changing it. So if we are not changing the frequency based on the formula there, it is the same metal that it is there. So the work function, it is going to be there. So that means The only thing that you are going to change, the speed of an electron, we can see there, it is saying half mv squared max. Immediately it's saying max. There is nothing above max. So you cannot change the velocity. So the only thing that we are going to change, it is going to be how many are you able to take out of, how many electrons are you going to take out of the matter in a particular time. But the energy is not changing because it's depending on the frequency. So we have to look at that. Hence, this last bullet, it is very important. What is happening as we change the frequency? What is happening as we change the intensity? Now remember, the intensity is of the same line, but the frequency will give you different. And then we can see from that formula that your energy, because H is a constant, your energy is directly proportional to the frequency. So the higher the frequency, then the higher will be your energy. So we need to talk to this and then check. And colleagues, this is another formula. Immaterial that formula there already, it is one of the things that will be saying, because W naught can be a part of the frequency. Let us look at that particular graph. It is going to be a straight line. That is why we are giving you, or the question is coming into that, and then there are these straight lines that are coming in. So let us go and prepare our learners with the interpretation and drawing of the graphs. Every diagnostic report is talking about interpretation of graph and then drawing of graphs. So let's try to help our learners, because that's where the marks are coming from. And then the last part about this one, colleagues, it is also the 2 marks or the 3 marks that you are having and that you are ignoring, which is going to be your emission and your absorption spectrum. Colleagues, they are very easy to can get. They're talking about energy transition. So let's help our learners to look at the absorption and then emission spectrum. And then the difference there of colleagues. For emission, it means we have to have a light that it is going through a hot, already it is hot. So there's nothing that it is going to absorb. So it is going to lose it. But with the cold, it is going to absorb. And then as it absorbs some of those, then there will be some spectral lines or the patterns that will be coming in. As we change the next slide, that number, that it is there, that we are able to can see from what we are having with the learner. So that explanation, it is very important, even though it is 3 marks, but we need it for our learners to understand what is it, why are we using a cold gas, and then why are we using a hot gas for the 2. And then that will maybe make it an explanation to be very easy for our learners to can see to it, what is it that it is coming out of this particular part. So this is the explanation that I was talking about, that it is only about the atomic spectrum and energy transformation. So let our learners get these 3, and then the 3 marks will be there. And then without much ado, I know I've taken about 15 minutes more of your time, but there is a lot that still needs to be done, colleagues. And if ever maybe you are having something that you want to ask, put it in with whoever. Our assistant advisors are there, our experience markers are there, having internal monitors, senior markers, everybody, colleagues. We are in this together. You know, together, each achieve more. A team, we are everybody, colleagues. So I want to take this opportunity in thanking you, to thank you heartily for the efforts that we have put in throughout the year, and also for the parts that you are still left. We have not yet arrived. We are having a bit that we are going to do. I know, colleagues, I didn't talk much about, but I showed you that at least we can have about plus or minus where we can get the marks and then how we can get the marks. So colleagues, let's work on them, especially these marks in multiple choice, where we are having definitions, where we are having the relationships, the graphs, how we draw them. Those are the marks that our learners need to come up with. Get them, the free body diagrams here and there, get them. the equations, they get the marks. I showed you the 27 marks out of only the definition and the equations. Now we add the 4 to the 27 for the free body diagram, we end up with a 31, and then we are running short of 14 marks, of which the 14 marks, here and there, there will be a substitution. So basically, colleagues, even those learners who don't think they can get 45, let's try to help them and show them that there is still some light. There is some marks that we can still get. And then, colleagues, may the good Lord bless you and help you and give you strength to go through this last lap of our work, as we are going to enjoy the other parts of this. Thank you very much, Ntate Nambane, as you go to the next slide. Over to you, sir. Ntate Nambane, the presentation is with you. Though it is not on PDF, we can even now, Baba, just say it in the groups. We don't have much that we are hiding. There is nothing. It is as it is. You can hardly see that. Yes, Baba. No problem, Baba. Baba, Mr. Namban, did you share the register or you didn't? Okay, no, it's fine. All right, no, it's fine. No, okay, Baba, sure. Thank you very much, Baba. Thank you.